Okay, so as Patrick mentioned, it is, you guys probably noticed, mass and the max angle value really don't matter in terms of a pendulum's period. The only thing that does matter is the length of the pendulum, and I want to show you briefly why that is. So for pendulums, torque is equal to negative mass times g times the length of the pendulum times theta. That's for small angles. So this is very similar to when we're talking about springs, as you guys are probably familiar with. Force is equal to negative k times the displacement of the spring. So also similar to this in springs, where omega is equal to root k over m. You have a very similar equation with pendulums, which omega is equal to mgl over the inertia. So mgl, much like k, is acting as a constant with a given pendulum in a specific set of conditions. And inertia is a lot like mass, resistance to acceleration, except it's rotational. So for a simple pendulum in which there's a point mass at the bottom of it, which our experiment pretty much was, this simplifies mgl over ml squared. L's cancel out, m's cancel out, leaving you with an angular frequency that is equal to root g over L.
As was seen in the experiment, the value of the mass did not affect the period of the pendulum. And this is because of the explanation that Paul gave, where angular velocity is equal to root mgl over ml squared, and the masses cancel out, thus negating the value of the mass in the pendulum equation. It was also shown in the experiment that the value of theta was not important for the period of the pendulum. And this is because although a greater value of theta provides a greater acceleration component due to gravity, the distance that it has to travel is balanced out. So a smaller distance coincides with a smaller gravitational component of velocity, whereas a greater distance is also seen when there's a greater component of gravitational acceleration. So one can see from Paul's equation that angular velocity is equal to root g over L. So if we manipulate this equation a little bit, you can square both sides, take it out. It's easy to see that angular velocity squared is equal to g over L. Thus we can see that the angular velocity squared is inversely proportional to the length. Thus, a greater length will provide you with a smaller angular velocity. And this is why the greater length of L, provided that we're all on the same planet with the same gravity, would give you differing periods for the pendulum.